In this video, I want to give some examples of tangent line problems that involve trig functions. So our first example is this. It says, give the equation of the tangent line L to the function f of x equal to 2 times sine x when x is equal to pi by 6. Well, as always, a tangent line L to y equals f of x at x is going to contain the point x f of x, and its slope is going to be f prime of x. So let's write that down in this case. All right, so L is going to contains the point pi by 6 f at pi by 6, which is pi by 6. What's f of pi by 6? Well, f is 2 sine x, so f of pi by 6 is twice sine of pi by 6. All right, so what's this then? This is pi by 6, and what is sine of pi by 6? Well, that is the y-coordinate of that point on the unit circle at pi by 6. Okay, so what is that going to be? Well, the y-coordinate of that point on the unit circle at pi by 6 is 1/2, so sine of pi by 6 is 1/2. All right, so this is 2 times 1/2, which is 1. So our point on our tangent line is pi by 6, comma 1. So, as we said, our tangent line L then to f of x at pi by 6, it's going to contain the point pi by 6, f of pi by 6, which we now know is pi by 6, 1, and has slope, so L has slope m equal to the derivative of f at pi by 6. All right, so what's f prime of pi by 6? Down. Well, f prime of x is equal to, well, our function is, if we go up again quickly, it's 2 sine x, so the derivative of f of x is 2 times cos of x. X is equal to 2 times cos x. So what's m? In this case, it's equal to 2 times cosine of pi by 6. That's f prime of pi by 6. What's cosine of pi by 6? Well, it is the y-coordinate of, cosine of pi by 6 is the x-coordinate of that point on the unit circle at pi by 6, and that is root 3 over 2. Okay, so this is 2 times root 3 over 2, twice cos pi by 6, which is equal to, I guess I should be using my yellow, equal to root 3. All right, so where are we at? Our tangent line L, it contains the point pi by 6, comma 1, and its slope is m equal to root 3. Well, if we have a point and a slope, we can give the equation. So, therefore, L has equation, what is it? Y minus our given y value. Given y value is 1, so y minus 1 is equal to our slope being root 3 times x minus our given x value. Given x value is pi by 6. So minus pi by 6. And what's this then? Well, rewriting this, we can write it as y is equal to root 3 x minus pi by 6 plus 1, or if you want to go one extra step, y is equal to root 3x minus root 3 pi over 6 all plus 1. Okay, so that's the equation of our tangent line in this case, done the same way as determining the equation of any tangent line to the graph of a function y equals f of x. The only difference here was that our f of x involved a trig function. Now we can differentiate trig functions, so now we can find equations of tangent lines to functions that involve trig functions. Okay, with our next example, we're being asked to find those values of x where the graph of the function f of x equal to x plus 2 sine x has horizontal tangent lines. Well, as with any function, y equals f of x, and I'm just drawing some random function here, we know that we're going to have horizontal tangent lines when the slope of those tangent lines is 0, because the slope of a horizontal line is 0. All right, a line is horizontal if and only if its slope is 0. Well, also, we know that the slope of the tangent line to f at some value x is equal to f prime of x. So what are we looking for? We're looking for where f prime of x is equal to 0. All right, so let's just write this down. F has horizontal tangent lines exactly when or exactly where, maybe I could just write if and only if f prime of x is equal to 0. So we're trying to find where f prime of x is equal to 0. Well, in this case, what is f prime of x? F prime of x is equal to, well, what's our function? It's x plus 2 sine x. So differentiating that, we're going to get 1 plus 2 times the cos of x. So let's write that down. So we've got, 1 plus 2 times cosine x. And we want to know where that's equal to 0. Well, that's going to be equal to 0 exactly when cosine of x is equal to minus 1/2. So this question is now just about determining when cosine of x is equal to minus 1/2. So let's do that. All right, well, that means that what we're looking for are those places on the unit circle where the x-coordinate is equal to minus 1/2. All right, so here's 1, our unit circle, and we're wondering when is this x-coordinate equal to minus 1/2. Okay, so we're looking for those points on the unit circle where the x-coordinate is minus 1/2. In other words, we're looking at for this point here, and we're also looking for this point right here. At these 2 points on the unit circle, the x-coordinate is going to be minus 1/2. Well, you might begin by remembering where is cosine of x equal to 1/2? Well, it's equal to 1/2 right here, and that is the angle pi by 3. So if this is the angle pi by 3, then this angle here is pi by 3 plus another pi by 3, which is 2 pi by 3. And this angle down here is equal to, well, we've added one more pi by 3, and then one more, so we're at 4 pi by 3. So this is the angle 4 pi by 3. Okay, so cosine of x then is equal to minus 1/2 when x is equal to 2 pi by 3 or 4 pi by 3. So let's write that down. X is equal to 2 pi by 3, or x could equal 4 pi by 3. So those places. But notice that the x-coordinate, so looking again at our unit circle over here, the x-coordinate is going to be minus 1/2 if we take this point here and we travel around the circle once, or forwards, or backwards. In other words, if we add or subtract 2 pi. Or we could go around the circle twice, adding 4 pi, or backwards twice, subtracting 4 pi, and so on. So, to give a complete answer, we can write this as x is equal to 2 pi plus 2k pi, or x is equal to 4 pi by 3 plus 2k pi, where k could take the value 0, plus or minus 1, to travel around the circle at once, forwards or backwards, plus or minus 2, and so on. All right, so that solves this problem. The thing to remember is that in trying to find where this function had horizontal tangent lines, we just needed to find where f prime of x is equal to 0, and this is always the case. And we've done, in fact, examples like this before in class. The only difference here was that our function now involved a trig function. Because we can differentiate trig functions, we can now find where functions that involve trig functions have horizontal tangent lines by solving for where f prime of x is equal to 0.